Guys, this is lesson 3.4, December 14th, I believe. You guys should have gotten a classwork from a sub. It looks like this. You can follow along in the notes with this. It goes pretty much hand in hand like usual. And today we're doing exponential growth and decay. So here's your picture of a Tyrannosaurus Rex trying to draw exponential growth. Okay. Types of growth and decay problems. Normally in class I was going to have you guys Google it. Since you're not here, don't worry about it. We'll go through plenty of examples where you'll see different types of growth and decay problems, but there's more than just what you'd commonly think of, I guess. And this is the formula we're pretty much going to use today, so we're going to break this down first. So a of t is equal to a sub 0 and then 1 plus or minus r, and this is to the t power. And if you notice, from last class we did y equals a times b to the x. This is the same thing, right? A is now this a sub 0, and then b is going to be the same thing as 1 plus r or 1 minus r, depending on the problem. And instead of x, we just have t. So it's the same format. This is your a, and then this whole thing is the b, which is the rate, more or less. So it's the same format, just a little bit different in context of real-world problems. So a of t is going to represent an amount of something at some time, right? At whatever time t you plug in for, the amount is going to be what the whole thing is equal to. Same thing as the y. Amount of bacteria, amount of money, amount of population, amount of something. A sub 0 just represents and usually when the sub 0 means, it means initial. So a sub 0 represents the starting amount or the initial amount. T, as you can probably assume, t is a time interval, so it represents not necessarily how much time is involved in the problem, but how many periods of time that go by, and we'll see some examples of that. It depends on the wording of the problem. If it's 2 years, probably is going to be that you're going to plug in 2 for t, but it could be different depending on what the rate is for. A positive t, right? So if t is positive, that's just going to represent a future amount. So maybe in 5 hours, maybe in 5 days, maybe in 5 years. But if you actually plug in a negative exponent for t, right? So if you plug in a negative t, it's almost like going back in time and figuring out how much would have been there based on some given information. So if it's a negative t, you can actually go backwards or find a past amount. You don't change it to a 1 minus if it was 1 plus. That has nothing to do with past amounts. Negative exponents would tell you what something was in the past. We'll see some examples of that. R, as you might imagine, also represents a rate. So it's either going to be a growth rate or a decay rate. That's just the rate that you're going to plug in, and then it's expressed as a decimal. So usually in context of word problems, R is given to you as a percentage, 5% growth, 2% growth with 1% decay. You need to change that to a decimal before you plug it in. And then a positive R value, right? So that would just mean 1 plus R, shows growth. So basically, if it's a problem that's involving something growing, exponential growth, you would use 1 plus r. That's why it's 1 plus or minus. And if the rate is decaying over time, you would show decay. So 1 minus r, right? So decay is 1 minus r, growth is 1 plus r. In the word problem, you'll be able to figure out if it's growth or decay. So here's a typical question. Population. Right, we have the population of a small town is currently 89,000 people, and it's increasing at a rate of 1.8% per year. So increasing tells you that we are exponentially growing instead of decaying, obviously. So this unit is calculator based, so you can take out your graphing calculators if you haven't already. And what we want to do is just predict the population in 2 years. So it's 89,000 people right now. We got the rate. We have the initial amount, which is 89,000. And we have a time interval, which is 2 years. So it's a pretty straightforward problem. If we remember our equation, it's a of t is equal to a sub 0, 1 plus or minus r to the t. Now in this case, because it's growth, it's going to be 1 plus r. We don't need the minus. And basically, The A of t is our initial amount, so that's going to be 89,000. And the rate is 1.8%. So it's going to be 1 plus, not 1.8 because that's as a decimal. We need to convert it. I mean, that's as a percentage. We need to convert it to a decimal. So 0.018. And then to the t. Now, t is a time interval. So it says in 2 years, and the rate is per year. So that means there's 2 time intervals that pass, because if it's 1.8% per year over 2 years, that's 2 time intervals. So we're going to use a 2 for the exponent. Right? Now, if this said 1.8% per 6 months, that would mean 4 time intervals would happen in 2 years. So you'd actually use 4. So it's not just because it says 2 that it's 2. Usually the rate is always per year. And this is years 2, so it's just 2 intervals that happen. And after that, just type it in your calculator and you're pretty much done. So we have 89,000 and 1 plus 0.018, and that's going to be to the second power. And then your answer is 92,232.86. So we'll write that down. Well, actually, we'll just copy it right in there. Okay, now in this case, you might think we want to round to 233 people, but you got to kind of think of it. You know, it's the population is growing, so in 2 years, in exactly 2 years, there will be 92,232 people. This next person has not quite been born yet, so you actually don't want to round up if it's population. Right? It's really only specific to population problems. So we actually want to keep our answer at 92,232 people. And that's one of the examples where you don't want to round to the nearest, right? If you're on it to the nearest, it would be 233. But if it's growing population, you don't want to round to the nearest because that person hasn't been born yet. Same thing if it was like the amount of bacteria. If the bacteria hasn't been created yet, round down. You know, money, most things you just round to the nearest, but this is an example where you want to round down. All right, second question. What would the population be 5 years ago? Right, so the initial amount is still the same. It's 89,000. The rate is still the same, right? It's still 1 plus. It's still exponentially growth. It's increasing over time. So it's still 1 plus. Just because you need to go 5 years in the past, most common mistake I see is kids change it to a minus. It's not minus. It's still growth. So it's 1 plus 0.018. The difference here is since it's 5 years in the past, we want to use -5 as an exponent, not +5, -5. And that's it, right? So everything else is the same. On your calculator, you can actually hit second enter, and it retypes the whole thing for you. And we just want to use an exponent of -5. So 5 years ago, based on that information, it was around 81,405 people. And that's it. Now the other type of a question which you could see, right? So far in both of these, we've solved for A of t. I could give you A of t and you could solve for the initial amount. You usually don't see that. But you could solve for the rate or for the time. In this case, we're going to solve for the time, right? The key is it says when, right? So that tells you you're going to be solving for t, since t is the only variable that involves time. So let's set it up first. So we have A of t, which is the amount. This is the same question, by the way. The question is, when will its population reach 150,000? So A of t, we want that to be 150,000. That's what we want to set it equal to. So we have 150,000 is going to be equal to the same initial amount. That hasn't changed. It's still growth, and that's never going to change. And the rate is still growing by 0.018, or 1.8%. But the thing that we're solving for here is t, right? A when. We're trying to figure out what year is it going to, and how many years is it going to reach that, right? So what you notice is you have two sides of an equation. The goal is to get t by itself, right? So you probably want to get this thing with the parentheses by itself so that you're closer to getting t. So what I'm going to do first is divide both sides by the 89,000. So divide by 89k or 89,000 and divide by 89,000. So these cancel. And on my calculator, I can do that. 150,000 divided by 89,000. The same thing as 150 divided by 89, since the three other zeros will cancel. All right, and I get 1.685, dot, 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 dot. So on my thing here, I'm going to put 1.6, there's dot, dot, dot. I want to keep all of those decimals, right? So I just put dot, dot, dot to show me that I need to keep all those decimals. Equals 1 plus 0.018, which you can actually just do that math because it's in parentheses, so it's 1.018 to the t. Now the problem here is this floating exponent, right? How on earth can you get this exponent down so that it's on the same level as the other numbers? Because you can't really match the bases here like we did earlier in the unit. 1.68 dot 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 is never going to equal 1.018 to a clean exponent. So if you remember from last year, this is where we're going to take into account logarithms. So what you can do is if you need to get an exponent down, you can take the log of both sides, or natural log, we'll just do log for now. And what that does is once you take the log of something, the exponent can come down. It's called your power rule. And now it's no longer an exponent, right? So just to rewrite it, it would be the same thing on the left side, except it would be log of 1.6 on and on and on, whatever I had in the calculator, is going to equal, and then the t comes out in front, times, t times equals t times log of 1.018. So the t comes out in front, which means you're only going to have to get this by itself by simply dividing both sides by log, which is just a number, it's just an operation of 1.018. Whoops. 0.018. And if you did it to one side, you got to do it to both sides. And that would cancel these out, and then voila, you've gotten t by itself. So we have to do this on the calculator. So I think the last thing on my screen is this 1.608. So first things first, I'm going to take the log of it. So log of second negative sign, we'll take the log of this answer for the last one. That's my numerator, so 0.226 is this, so it's 0.226 divided by log of 1.018. So I'm just going to divide by log of 1.018, and that is what t is equal to. So you get 29.2601. So answer is going to be 29.2 dot dot dot. When 29.26 years, that you can say that, but nobody really says that in the real world, right? But if you take like 0.26, like cut off decimals here, 0.26 times 12, I mean it's like 0.25 times 12. It's basically a quarter. Yeah, it's like another, not quarter. It's a quarter of a year, actually. I'm sorry. So that's like 3 months, right? 3.12 months. So just to make it sound a little bit nicer and cleaner, I would say 29 years. Let's spread this out. 29 years and 3 months. I would say that's probably a better sounding answer than saying 29.26 years. 29 years, 3 months. That is when this town is going to reach a population of 150,000 if this growth stayed exactly the same. All right, and then the only other type of question, just let me think here. Okay, so that's one we're solving for t. Again, the key here is take the log of both sides. Then just keep your work organized. You can replay this video if you're getting weird answers on your calculator, but just keep it all organized, do it step by step, and you should be okay. The only other question I think you're going to see in the activity is a half-life problem, or you might see in the homework. Half-life, I don't know if you've dealt with it in chemistry, but it's basically the amount of time before half of something is gone. So if you take medicine, its half-life could be 2 hours, which just means after 2 hours of time, half of it is gone from your body. Right? Your body's kind of got rid of half of it. So it's the amount of time it takes for something to be cut in half. So we have this chemical iodine 131, right? The 131 doesn't have anything to do with the math. It's just the name of the chemical. It's used to destroy thyroid tissue for overactive thyroids. Okay. The half-life of iodine 131 is 8 days. So if you get a certain amount of it, 8 days later, it's going to be, half of it is going to be gone. 8 days after that, another half is going to be gone, and so on and so forth. So if a hospital receives 200 grams, how much is going to remain after 32 days? Okay? So without even setting this up like the regular problems, I think we could probably do this. If you think about it, right now you have 200. And then if you think about it, 8 days later, right, so I'm going to put 8 under here because that's 8 days. 8 days later, how much would be left? Well, it's a half, so that would be 100. And then if you think, okay, another 8 days, how much is going to be left if you had 100? Well, that would be cut in half again, and you'd have 50. If you think about, okay, another 8 days, which is a total of 24 days, half of 25, you'd have, half of 50 is 25, you'd have 25 grams left. And then if finally you went another 8 days to get to your total of 32 days, you would have 12.5 grams. And that would be your final answer. Now, how do we do this? Setting it up like this equation, right? And we can make it a lot easier for us. And we can do it, like if I said 33 days, notice how 33 days, how would you do that? Because it wouldn't cleanly fall into like a period of 8. So it's pretty simple on your calculator. It's the same thing, right? What your initial amount is going to be 200, right? So it's 200. And then it's going to be 1 plus or 1 minus something. If you think about half-life, it's decaying, right? It's being cut in half. So it's 1 minus some rate. And then here, if you're thinking how many time intervals goes by, it's not 32 days, right? So this is where, even though it says 32 days, it's not like you're plugging in 32 days. It's a time interval. So how many times does this process occur, right? So if you think about it, 8 days, each half-life is 8 days. And I'm looking to figure out what it is after 32 days. So basically, I'm thinking, how many intervals happened? Well, over the course of 32 days, if each half-life is 8 days, that means 4 time intervals have passed, right? 4 half-lives have happened. So the exponent is actually going to be 4, right? That's 4 times these things is decayed. So now it's just a matter of figuring out the rate. Well, it's called a half-life. The rate is 0.5, right? Half of it's decaying every half-life. So that's just 1 minus 0.5. So it's always going to end up simplifying to 0.5. You don't even have to write 1 minus 0.5 because 1 minus 0.5 is 0.5. So on your calculator, that should give us the same exact answer. And if you see here, it does, right? So 12.5 grams. Now, if I said after 15 days, this is a good example because you couldn't really do this on your, you couldn't do this out the same exact way. So it's the same thing. It would be 200 is your initial amount. It's going to be 0.5 for 1 minus 0.5. And now your exponent's not so clean, right? If it happens in 8 days, after 15 days, 1 full half-life has happened, and then almost a second one has happened. 16 days, you get another one. So what you can always do is just do, okay, it's 8, which is 1, and then there's 1 in 7 days in there. So the exponent, you can just keep it as a fraction. It's 15 days, and then every half-life is 8. So you can write your entire exponent as a fraction, just like we could have written this one as 32 over 8, just reduced to 4. This one we can just write it as 15 over 8, and then we should be good. So here, I'm just going to say 15 divided by 8. Make sure if you don't have this elevated exponent that you use parentheses. And we get 54.5 grams. And that's that answer, which should make sense, right? Because if you think about it, it's pretty, like after 2 half-lives, as we've already seen, it should be down to 50, right? You had 200, so after 1 half-life, it's 100. After another one, it's 50. So this is almost, 16 days is almost 2 half-lives. It's not quite, so you should have a little bit more, which we do. 54.5 is a little more than 50. You should always be doing these common sense type of checks. And then 3 days ago, right, so if it was decaying on the way to the hospital or something like that, it would just be the same thing. It stays as a half-life problem, so 0.5. But 3 days ago, we're going backwards in time, so it's negative 3/8. So we should have more than 200 if it's been decaying. We're going backwards. And second enter. I'm just going to do negative 3. And we get 259.4. So 259.4, and then it's measured in grams. And that's pretty much all the types of questions I think you would see. So you're going to do an activity next, and you're just going to do it, I think, in the groups that you have. Yeah, your groups of 3. So it should look like this. This is what the sub should be giving you. You just need 1 per group. I don't think you're going to finish. So just get as much done as you possibly can, because I don't want to give you too much more time when I get back. Get as much done as you can. The homework the sub will also hand out should look like this, just a separate, kind of like your activity, just separate. And then that'll do it. But always make sure you use a common sense check, CSC, right? The good thing about these word problems is they should pass a common sense check, right? If it's not in context of a word problem, it's hard to tell if your answer makes sense. But in these ones, right, just like we did with this one, 54.5, okay, that makes sense. It should be a little more than 50. Do those kinds of checks just to make sure that you're doing it right. But I'll let you get to the activity, and then homework is what I just showed you.